The sea, once it casts its spell, holds one in its net of wonder forever. Jacques Cousteau. Watch to the end. The most underestimated anatomical feature appears at the very end. Eurypharynx richardi, commonly known as the gulper eel, inhabits depths typically between 500 and 3,000 meters. In the bathypelagic zone, where food is rare and unpredictable, this species represents one of the most extreme examples of anatomical expansion. Its most obvious feature is its mouth. The oral cavity can expand to proportions far exceeding the rest of the body. The jaws are elongated and supported by flexible skeletal elements rather than rigid reinforcement. Unlike predators built for bite force, Eurypharynx richardi is built for volume. The body behind the head is surprisingly narrow and whip-like. Muscle mass is reduced. Ossification is minimal. This contrast between massive anterior expansion and slender posterior form is not accidental. It redistributes mass while preserving buoyancy. The stomach is also highly distensible. When a rare feeding opportunity appears, the eel can engulf prey nearly equal to its own body size. In an ecosystem governed by scarcity, missing a large meal can be fatal. Oversized capture capacity increases survival probability. Its eyes are small, consistent with life in darkness. Vision plays a limited role. Instead, the species relies heavily on mechanosensory and possibly chemosensory detection. One of its defining traits is the bioluminescent organ at the tip of its tail. This photophore emits light, likely functioning as a lure. In darkness, controlled light emission becomes a strategic tool. Rather than chase prey, the eel may attract it within strike range. Midway through this analysis, remember Darwin's principle. It is not the strongest of the species that survives, nor the most intelligent but the one most responsive to change. Charles Darwin. Eurypharynx richardi did not evolve speed or armor. It evolved capacity. When prey is unpredictable, the best strategy is to be prepared for extremes. Now here is the rarely emphasized detail. The jaw suspension system is supported by elongated, flexible branchial arches that allow lateral expansion without proportional increases in bone mass. This means the mouth can widen dramatically while remaining structurally lightweight. Most summaries focus on the big mouth, but not on the skeletal engineering that makes such expansion mechanically viable under high pressure. Additionally, the thin skin membranes surrounding the oral cavity act like elastic storage material. They can stretch without tearing and then retract after feeding, minimizing permanent drag. Hydrodynamically, the eel drifts vertically, conserving energy. The elongated tail may stabilize orientation in weak deep-sea currents. The glowing photophore at the tip enhances encounter probability without requiring rapid locomotion. Reproduction follows the leptosphalous larval stage common to eel lineages. Transparent, ribbon-like larvae inhabit upper waters before descending as adults. This life cycle bridge connects surface productivity to abyssal specialization. Ecologically, Eurypharynx richardi occupies a mid-level predatory niche, consuming crustaceans and small fishes. It may itself fall prey to larger deep-sea predators. Even in darkness, trophic hierarchies persist. Its morphology may appear exaggerated, but it is mathematically efficient. Oversized intake, minimal structural investment, energy conservation. It does not hunt often, it hunts decisively. If this changed your understanding of deep-sea adaptation, support the channel. Like this video, subscribe for precise, research-based ocean analysis, share it with someone who thinks evolution favors symmetry, and write in the comments which abyssal species we should analyze next. Your engagement directly supports further high-accuracy content.